Welcome back to the terrain rendering series. Today we're going to integrate the tessellation pipeline into the terrain system. This will enable dynamic level of detail, which means that parts of the terrain closer to the camera will be rendered with more details and vice versa. Now, we've already implemented dynamic LOD in this series using the GeoMIP mapping algorithm without tessellation, but as you shall see, the new implementation will be much simpler. See the link in the video description for the GeoMIP mapping tutorial. Okay, we've covered tessellation in a couple of previous videos, so I'm going to assume that you are familiar with quad subdivision, which is what we're going to use here. This algorithm matches our terrain mesh very nicely because the original geometry is constructed using a grid of quads or patches, where every patch is tessellated into several triangles. The highest resolution is provided by LOD 0, and for each consecutive LOD, we decrease the number of triangles within the same patch. This of course must be prepared before the game actually starts running, and is quite complex. We can use the power of the tessellator to dynamically subdivide the patch based on the distance from the camera. Instead of matching each grid vertex to the corresponding cell in the height map, we will start with a flat terrain, and in the evaluation shader we will sample the height map for the Y value of the vertex. The texture sampler in the GPU will interpolate the height between neighboring cells when the texture coordinates falls between cells and not on a specific cell. Let's see how to set up the system of a tessellated terrain. We begin with the vertex mesh. The basic element here is a 4-vertex quad, which will be fed into the pipeline as a single patch. Remember that tessellation works on patches and not triangles, and that a patch has one or more vertices up to some maximum. So this is a 4-vertex patch which happens to look like a quad. We will create a grid of vertices in the vertex buffer, and the index buffer will form patches from these vertices. By default, the distance between vertices is 1 unit, which might be a bit small. For GeoMIP mapping, I created something called the world scale, which was used to multiply the coordinate of each vertex and thereby scale up the size of the terrain mesh. I'm going to use it here for the same purpose, only that the value of the scale is going to be much larger. The tessellator is capable of generating an enormous amount of vertices, and you don't want them to be too close to one another. So try patches with the size of 64, 128 or even more. Of course, it doesn't have to be a power of 2, it's just a programmer's habit. Any value will work. The vertex itself is going to contain only 2 attributes, the position and the texture coordinates. The texture coordinates will go from 0 to 1, and the delta between neighboring vertices is of course 1 over the size of the grid in vertices. It has to be 0 to 1 so that we sample the height map correctly, but for the color texture we will scale up the coordinates by some value. Otherwise, the color will appear washed up. As I said, the basic terrain mesh is flat. We only need to calculate x and z while the y coordinate is 0. This means that the normals at this stage are simply pointing up, so we don't need them in the vertex buffer. We will calculate the normals later, based on the height map. You can find my implementation of the mesh in a class called QuadList. The code is pretty simple and you can review it offline. Okay, with the vertex mesh out of the way, the only thing we have left is to review the shaders, because this is where the main action takes place. So we start with the VS, which turns out to be the simplest of all the shaders here. It gets the position and texture coordinates and passes them along without any changes. Next up is the tessellation control shader, which also passes along the position and texture coordinates without any changes. But the TCS has an important responsibility, and that is to set the tessellation levels. In this case, since we are interested in implementing dynamic level of detail, it makes sense to set the tessellation levels according to the distance from the camera. The solution is to transform the vertex position to view space, after which the camera is located at the origin. This means that we can calculate the length of the view space vector, and this will give us the distance from the camera. But we have a problem. The patches share edges between them, and the tessellator will create a set of inner rings around the center of the patch, plus an external ring along the edges. If the tessellation level of two neighboring external rings is different, there will be cracks in the terrain, as we have discussed in geomap mapping. To avoid cracks in geomap mapping, we made sure to use the same LOD on the two sides of a shared edge, and the solution here is the same. We have 4 tessellation levels along the external edges, plus 2 in the center of the patch. We have to make sure that the left tessellation level of one patch is the same as the right tessellation level of the corresponding neighboring patch. The same goes for the other 3 edges. In the case of the patch center, we don't have such limitations, but it makes sense to use a similar tessellation level, so we will use the maximum of the 4 edges. Matching tessellation levels of neighboring patches is simple. We will set the level based on the distance to the closest vertex on that edge. Since the neighboring patches use the same vertices, this comparison will provide the same result for both of them. We will map this distance to a range of 0 to 1 using a configured minimum and maximum distance. Everything which is closer than the minimum distance will use the maximum tessellation level, which will provide the highest level of detail. Everything which is further than the maximum distance will use tessellation level 1, which provides the lowest level of detail. Everything in between will be smoothly interpolated. This will help us reduce the popping effect, which is often prevalent in such algorithms. The implementation in the TCS is pretty much the same as the theory. First, we transform the 4 vertices to view space. Then we calculate the length of each view space vector. Notice that we only use XYZ to get the correct result. Next, we do a simple linear mapping to 0 to 1. The result is clamped to 0 to 1, so we don't get overflow or underflow later on. We can now calculate the tessellation level for each edge by taking the minimum distance between the 2 vertices on that edge. The result is used to interpolate between the maximum and minimum tessellation level. We use the GLSL mix function for that, and notice the order of the parameters to this function. Distance 0 is mapped to the maximum tessellation level, and distance 1 is mapped to the lowest level. We can now set each tessellation level to the proper location in the test level outer array. Finally, the 2 inner levels are set based on the maximum between the 2 edges, which are parallel to that level. The next stage in the pipeline is the evaluation shader. We start by extracting the results from the tessellator, which are available in the test coord internal variable. We use them to do bilinear interpolation between the textual coordinates of the patch. The result is used to sample the height from the height map. Remember that in the geomap mapping algorithm, the height map was used offline to generate the terrain mesh at different LODs. But now the LOD is calculated dynamically in the shader, so we have to sample the height from the corresponding location in the height map. This means that we have to bind the height map for reading and set up a sampler 2D uniform variable for that. Next, we do the same bilinear interpolation to get the local space position of the output vertex. And finally, we offset the y-coordinate using the height and do the usual view and projection transformations. The last shader is of course the fragment shader. This one is very similar to the shaders from the previous tutorials, but I want to point out 2 important differences. First, the textural coordinates go from 0 to 1. As we saw, this is so that we can sample the height map. But for sampling from the color texture, we have to scale up the coordinates using some factor, which is provided by the application. The second issue is of course the normal vector. I mentioned earlier that due to the dynamic nature of tessellation, we can't pre-calculate the normals and put them in the vertex buffer as we usually do. But we can use the height map for that by sampling the height at neighboring pixels. We need to get the height on one pixel to the left, right, top and bottom, and then use this function to calculate the normal at the current pixel. Explaining this formula is a bit out of scope for this tutorial, so I'll leave a few links in the video description with some background. How do we get the height at the neighboring pixels? Well, one method is to calculate the delta between pixels in texture space and add or subtract it to the current coordinates. The delta is of course 1 over the number of texels. There is actually a simpler method, which is to use texture offset instead of the usual texture GLSL function. Texture offset takes a third parameter, which is a 2D integer offset vector. This offset will be applied to the texture coordinates after they have been converted to texture locations, and the height will be sampled from the new location. Using a combination of 0, 1 or -1, we can easily move to the left, right, top or bottom of the current pixel. And that is it. Thank you so much for watching, and I hope to see you in the next tutorial.